We're going to continue on with our comparison effort here. So I'm opening up Electronics Desktop, and I'm going to find this archive that I created. One of the earlier lessons that we had that was recorded on setting up a point charge in Maxwell. If you remember, we set up a solution and we evaluated some electric fields and we created that archive. So I've got this name that I used with my initials appended to it. And as soon as Electronics Desktop opens, we're going to restore that archive and make some changes to it. So we'll be able to hold on to that original version. So when Electronics Desktop opens up, I really don't need this folder open anymore. I should be able to browse to that window. So I'm going to go to File and choose Restore Archive right here. And the browser window comes up and it's asking me to point to the archive in question. So that's the one that we'll bring up. And we'll go ahead and leave it right here exactly where it was as far as the directory. But what I'm going to do is change the name. The initial name of the project was Intro Static Charge 1. And I'm just going to give this one changed number 2. Give this a second to unpack. And this should look familiar to you. If you remember, in this design, we had basically just two geometry objects. One's the vacuum, the air box. That's where our solution is residing, and we have the sphere, which is what we put our charge on. So it's not exactly a charged particle. It turns out that it's a sphere. If I expand this out, I can look and see the properties, and I can see we defined it as a radius of 1. So it'll be interesting to see some of some of the differences that we see in the calculations as we proceed on with this exercise. If you remember, we had excitation set. The charge was given 1 coulomb. The voltage on the air box boundaries was given 0 volts. So that's essentially the equivalent of looking at the space in the far field region, where the universe is, we're kind of approaching infinity. If you remember, we also put these field overlays together. I have enabled mine. If you right-click, you can go to plot visibility to get them back on. So I'm just going to choose. You can see the vector E field there. We did an overlay, and we also did the magnitude. If you're not seeing those results, it's possible that when you go into your results panel, you might go to solution data and verify that you actually have values here. If you don't have values here, maybe now's a good time to go back to simulation and then hit analyze to get caught up. So we will proceed now. What I'd like to do is calculate field values instead of just trying to pick numbers off of these visualizations here with magnitude and vector. What I'd like to do is actually create points in the solution volume and report exactly what the magnitude of the field is on that point, so we can make comparisons to what we did with the analytical and numerical calculations. So to create a point, I'm going to move into the Draw tab. We've been here before to create the sphere in the box, but I'm going to actually choose this object here. So I'm going to click on the button that says Draw a Point. And you'll notice in the bottom left, it's asking me to enter the point position. Now, there's a couple ways to do this. I could literally just drop it anywhere I want in the XY plane. If you notice here, the grid is aligned on basically Z equals 0 in the XY plane. I could just choose to have it snap to the origin, and then what I can do is make an adjustment. So right now, you'll see I got a new list of, I have a single point in my point node. And the position, it looks like I actually guessed right, and I dropped it at a location of x equals 1, and y and z are both equal to 0. So if I zoom in, you'll see that the point, it's 1 millimeter, so that's exactly the radius of the sphere. So let's go ahead and calculate the first point there. If your point is not there, then just go ahead and, when you select it in Properties, you can just make the adjustment by typing the number in directly and hitting Enter. So now what I'm going to do is use our Results tab, and I'm going to do a field report. When I click Field Report, there's a number of different modes, and I think what I'd like to do first is just try the data table. So when I choose data table, you'll see here you've got various things inside the report. I've got a context section. I've got categories, quantities, and functions. You know, most of the time we'll be using a lot of the defaults as we get started, but as we get a little bit more sophisticated, we'll be changing some of the details. And I'll try to explain the complexity of these things as we go. For now, all I want to do is show you that we can actually assign values of these reports to objects, and one of them is going to be our new point. So go to the context section and change the geometry to 0.1, and when I do that, you'll see these quantities open up now. And the one that we want right now is going to be mag-E, which is short for magnitude of electric field. That's the thing that we've been calculating in the previous videos to this section. So with that, I'm just going to, I don't have a report yet, so if you pay attention to what happens here, this results node is about to get you know, something added to it as soon as I hit new report. And here it is. It just gives it a default name of calculator expression, and it tells me that it's mag-E. I can keep this window open, or I can close it, because what I really wanted was the value that was associated with that point. So I'm not going to worry about this column at the moment. I know that this value is assigned to 0.1. That was the object that I chose, and it's telling me what that value is. So if you go back to our calculations that we did analytically in the previous videos, you should find that the number that you see on the screen here should be very close to those values that we calculated, you know, either by hand with the calculator or the ones in Excel. Now, I'd like to evaluate another point now. You may have guessed we're going to evaluate a point at 1 meter, because that's what we were doing with the other examples. To get back to the view, just a little bit of bookkeeping on you know, manipulating inside of Maxwell. Don't kill this big X. Don't hit the big X up top on the top right. That's for electronics desktop. Everything would shut down if we did that. But as the insert, I've got this smaller X. That means the current view is the results window, and I can kill that view just by clicking it. I've got another view here. This is my 3D view here. I could also kill that window just as a kind of an overview of this, because I could always get it back by either double clicking on the thing that I want in the tree here, or I can go to view and I should be able to get it. I think I can get it in view. At least I thought I could, but I'm going to go ahead and double click instead. So I can always get the view back by doing that. And now what I'd like to do is drop a second point, and I'm going to make this 0.1 meter. So let's draw a point, and I can use the measuring, you know, feedback over here. As I drag the point, you'll notice that it tries to stick to certain things inside. As it sees like entities on it, like that's the face center, you know. Over here, it senses that there's corners of the cube. It might attempt to snap to that. What another thing that you can really do is that's very helpful is if I hold the X key down, it limits my movement to just the X-axis. So I want the distance from the point to be 1 meter. So as you've noticed by now, it looks like we're in millimeters. So when I get to 1,000, I'm just going to go ahead and hit the point. And now I've got 2 points. And I could even relabel these if I want, but it tells us right here in no uncertain terms where this second position is. So let's go ahead and plot the value on point 2, and let's see what we get. What I can do is I'm going to do it by double-clicking the calculator expression table. And now I've got my old point that shows up here. I'm going to right-click and I'm going to update report. Should, for some reason, it's not showing me the update window. Sometimes there's issues on the server. I'm gonna try. Oh, sorry, I meant to choose modify. So when I choose modify now, you may have guessed that I'm going to change my geometry now from 0.1 to 0.2, and now I'm going to calculate mag-E, and I'll this time I'm going to add I'm going to add the trace. I'm not going to apply it. I'm going to add it. So when I say add, and now I close the window, I should get my second value, and I get something else. I get this NaN, and sometimes you'll see that in computing and in coding. You'll get that ASCII representation, or I should say the character representation that stands for not a number. So it looks like something went wrong when we went to evaluate that. But I didn't expect to get a number. I wasn't sure what I was going to get because I kind of set us up for this. As you may have wondered, here I am outside of this solution space requesting a value, and you may have already thought that was a little bit suspicious, and that was really by design because I really want to drive home the idea that in this type of solver, this finite element solution, we really are limited to what was meshed up and solved. And I can see the full extents. I can get a representation of what was solved, by looking at these field overlays. And you can also there's other ways to gain insight as to what was solved as well. And what it means is that if had I set this boundary to go, and what this really means is that this technique, this computational technique, is only going to solve what I ask it to solve. And when we set this problem up the first time, we made the arbitrary choice to set the air box to be only 500 millimeters. So that means that our whole domain was limited to what's taking place inside that box of that size. Had I known at the time that I was going to try to solve for something that's further out, there's a couple of different approaches that I could have made, but I one of them is certainly to expand the size of the box to include that space. So what I'm going to do now is let's change the size of the box. And since I know I only want to go out in the x-axis, I'm going to choose to just change that solid so that the x distance is going to encompass my full 1 meter. So I'm going to say 1,000. My box has expanded. I can see my 0.2. Actually, I did that wrong because I forgot that the box does not start at the origin. The box actually started behind the origin, and I remember that that should have been an extra 250 millimeters. So let's go back to the create the box, and I'm gonna add 250 millimeters. And now we should see that the point is right there on the face. Now, you may have noticed over here these X marks have shown up. You'd also notice that if I go to plot visibility on any of these field plots, nothing's happening. So you might be thinking something's broken. If I go to results and solution data, there's nothing in my solution data. It's because I changed my original problem and everything basically got wiped. So all the field values that were stored inside that air box are now gone. So that forces me to resolve. So just make sure I didn't mess anything up. I'll validate. I'm in the simulation tab. And once that's done, I'm going to hit analyze all. And then we'll let this go, and I'll just pause until it's complete. Shouldn't be very long. Okay, so after just a couple minutes, we get new results. You may have seen some of those fields update. You get some pretty interesting looking field plots with the change that was made. But you'll see the basic structure is really about the same in the area that we looked at, and really going out through the entire volume. There are exceptions that you can see about the behavior as you approach those walls that we'll talk about in a second. What I'd like to do now, though, is let's take a look. Let's go back to our calculator table, and you'll notice that we recovered a value this time. So looking at the point on the in the adjusted model, that's one meter away, 1,000 millimeters. We previously had not a number, and now it appears to be something on the order of, let's just count them, 1, 2, 3, 4, 5, 6, 7. So it's about 9.9 times 10 to the 7. And if you recall back, that's actually a little different than what we had calculated. So you might wonder what's going on here. And there's actually a perfectly good explanation for it. Now, to illustrate this point, I'm going to do something else. I'm going to create a line, and we're going to plot the field along a line, much like we did with the Excel exercise. So let's choose the draw line. I can turn the vector fields off for now, and let's choose draw line. And the question that it's asking me is if I want a non-model object. It's allowing me to hold on to the results, knowing that the line doesn't really have to be part of the physics. We're not going to apply a charge to it or anything that's going to affect the physics. So for that reason, we're going to say yes, make it a non-model object. That's what that means. It's not used in the physics. So my results didn't get removed yet. So now it wants me to drop a location. I'm going to create the line from the center, not 1 millimeter anymore. I'm going to do it from the center of the sphere. If I zoom in, I can click once. And if I zoom out, I'm not clicking anything yet, but you'll see it's waiting for me to drop the second point. And what I'm going to do is, when I get out here close to the face, you'll see that the little cursor on the edge makes a change. It turns into this sphere, indicating that it found the center of the face of the edge of that air box, and it's basically giving me a chance to double click there to put the endpoint. And that's exactly what I'll do. It's not a single click, it's a double click, and that will end the line. So you can see the magenta object there, and it also showed up in my tree, and it's called a polyline. And if you wanted to change the location, just like the point, you're able to do that as well. It shows me the start and end points. There they are. And there's other things that we'll probably talk about later with the line. But right now, all we want to do is create a different type of plot on it. So I'm going to go to Result, and I'll go to Field Reports again. And this time, instead of choosing the data table, I'm going to choose this 2D plot. And I want to plot the results along my polyline. And I'm going to choose Mag-E. So it's really the same as what I was doing before with the point, but you'll see it's a very different type of form or report. And it even has a different indication on it. So let's close this out. And I'm going to change a couple things on the scale here. So one thing that you'll notice is that we certainly have data, but it looks like it's either all very high or zero. And it turns out that that's really more of an artifact of plotting extremely large values, a large range of values in what we call a linear scale. So what I'm going to do is change the scale by double-clicking on one of the numbers on the y-axis. And I can go to y1 scaling, and I should be able to change the type to log. Okay, and I'm going to hit apply. And you'll see what's happened here is you get a very different look for one thing, but the most important thing is that notice how the scale has really it's no longer linear. The major tick marks are moving up in orders of magnitude, and that's exactly what we asked it to do. So this would be the equivalent of writing out 10 to the log of some collection of numbers. And the log scale is made for that. It's made to put varying, dramatically different values, very high values to very low values, all on the same scale so you can see it. So it's essentially compressing, in a repetitive way through these different orders of magnitude. So we actually get to see a little bit of what's going on right now. So there's a couple of things that you might notice. I can zoom in and out. And if you remember, we started our plot at 0. We didn't start our plots in Excel or in the analytical calculations at 0. We started those at 1 millimeter because it turns out the analytical function for a point charge is undefined at r equals 0. It blows up, it goes to infinity. But keep in mind that our representation of a point charge in Maxwell 3D right now is actually a sphere. And it's totally valid to calculate the value at the center of a sphere. And I have questions about the accuracy of that value, but the fact that it is a number, there's certainly nothing wrong with that. You would expect to see some type of number, and you would also see this this linear behavior as you go from the center of the charge up to the shell, where as soon as you get past the shell and you're outside of that sphere, it takes on a very different behavior. We'll talk more about that later, but that's the reason why it does look different there. You might notice a couple of anomalies here. It's got this smooth transition, except for these, there's a couple of blips, and something really strange is happening here as we get out to this, as we get out near 1 meter. I can't explain the details of why it looks like that exactly, but I do know that plotting this point at the boundary is something that you probably wouldn't expect to be very accurate. So I set up an artificial boundary of voltage of 0 everywhere on the shell, including right where I requested the point. So this was another kind of a setup to sort of expose a concern when you set up simulation models. You want to be very careful to consider the boundary of the solution space and make sure that you're sampling in appropriate areas. So what I know is that the boundary being forced to 0 is going to artificially change those results in that vicinity. So if I really want the field value at 1 meter, it would be wise to give myself a considerable amount of buffer beyond that so that any of those artificial effects are going to be ignored in my calculation.
The last thing I want to do is export what we just plotted so we can compare it to our Excel calculations or any other calculator that you may have used for that. So all I did is go into the report space, and when I right click and choose export, you'll see that it's going to point to my OneDrive, and that's the chart that we did in the previous video, or I should say the Excel spreadsheet. I'm gonna name this the same as my project and call it, let's say, results. Let's just call it results from Maxwell. And now I'm going to choose to export uniform points. We're going to start at 0. That's the location on our line. It's in centimeters. I want to put it in millimeters. So if I bring the drop down, and you should be able to find millimeters in here, down here at the bottom. So make sure you started at millimeters. And I'm going to bring it to 1,000 millimeters. You want to stay in the same units. And let's do a step of 1 millimeter. So it should be clear what we expect to get. And now with that, I think we're okay to export now. So again, if you do this, make sure you point it to your OneDrive so you'll have access to it and not on the server computer. And let's just go for it. Okay. And let's verify. Go to my OneDrive. I should see what just came, and it's got the right date and time. So I'll right click on this. You'll notice that the format is a CSV. It says Excel, comma, separated value. It's different than an XLS file. I'm going to go open it now, if I can find open with. And let's go ahead and open it in Excel. So now we'll see this opens up just like the exercise we did building the expression in Excel. It looks like all of our data. It comes in with a header of distance in millimeters, and this whole column A is exactly that. That's our R value. And then we have magnitude of electric field. So you'll notice there's no expression here, right? When I click on these cells like we did before in the in the expression exercise, we had a formula. These are numerical values that were already calculated, so it's got no connection to how we really got the data, right? We have to keep track of that. So I'm going to leave it as an exercise now. We'll talk about this in class, but what I'm going to do is have the team who's in charge of plotting out the expressions in either a graphing calculator like Desmos or Excel. I'm going to have the computational team who works on the Maxwell model find a way to compare these two data sets, so we can find out what probably needs improvement, and we'll come back and iterate this. So we should see this goes all the way out to 1,000 millimeters, and sure enough, it does. So that's going to be the end of the exercise for now, and we're gonna keep talking about how to improve the data and which one of these data sets is more accurate, and things like that. So that's the end of the session. Thanks.